Hello everyone. From this video, I would like to start a new series video that is how can we implement the PID loop control via the Siemens i7-1200 and i7-1500 in TI portal system. I will use 10 videos to discuss this topic. Maybe someone will ask why we need 10 videos to discuss this topic. That's because the PID algorithm basically that is the core of the PID loop control. That is one discrete equation or an algorithm in one function block. Other than the PID control algorithm, we still need to set up the analog input, analog output. Also, you need to understand your control data system. You need to understand the actuators. For example, as shown in the screen, the actuator in this system, that is a motor drive circuit plus the motor system, because this motor drives the fan to cool the air. Also, you need to set up the analog input channels. That means you need to use the proper sensor to measure the temperature, to measure your variables, and then transmit to the analog input of the PLC system, and then use a scale to calculate the final input of the PID control system. That means when we talk about the loop control system, it's not only a PID controller, that is an entire loop control system. That's why I would use 10 videos to discuss this topic. If you just start from the PLC area, or if you just start to learn how to use a Siemens controller to implement the PID, it's highly recommend you look at the detail of these 10 steps. So I will introduce the step-by-step how we can implement the PID controllers using the Siemens controller. I will use one sample program which can be downloaded from the Siemens support website. So we do not need to totally from the scratch. We can start from this sample program. In the following videos, I will introduce step-by-step how we can set up the PID controller, how can we set up the scaling, unscaling about the analog input and analog output. But to help you to quickly build up the concept and understand how a PID loop works, I will leverage this sample program HMI project, because that HMI already built up the trained the I/O field to set up the PID parameters, gain, integral, and the derivative, so we can have an overall picture of how that control loops works. So that's why I will use this sample program. But in the following videos, I will still introduce the detail how we can set up the PID controller, as well as the analog input, analog output, the all essential parts of the PID loops. Alright, let's start. Firstly, let's copy this ID code, and then let's go to the Siemens support website to search this sample program. After you search the support.industry.siemens.com and search this ID from this search area, you will find this sample program. That is a PID control with a PID compact for SIMATIC i7-1200 series and i7-1500 series. The programming platform for those two series controllers, that is a TIA portal software. And the current version, that is a version 16. The PID controller inside this platform, that is a PID compact. It is compatible while using 1200 and 1500. So that means the PID control function block, they are the same using the 1200 and 1500. From this sample, it attached two sample programs. One is for 1200 controller, one is for 1500 controller. You can download them. Also, to better understand how this system works, you can download this document and learn how it works. So in this system, I will use this sample project for 1200 controller, because in my hand, I have one i7-1215 controller. This controller has two built-in analog inputs. They are 0 to 10 volts, and the two analog built-in current outputs. They are 0 to 20 milliamp. I also have one signal board that can configure the analog output, voltage, or current output. In this video, I will use this sample program as my base and change the controller to i7-1215 controller, and then download this program to the controller, set up the HMI, run this program, basically demonstrate how this sample program works. Since the PLC SIM software doesn't support the PID running in the i7-1200 controller, so if you don't have the hardware controller in your hand, you can download 1500 PLC project. and then run this PLC project in a PLC Sim advanced software to simulate the PID compact this function block. Alright, let's download the sample program and shift to the TI portal. Once we download the sample program, let's unzip this project. And I will use this i7-1200 project. And the sample project was built by TI portal version 15.1. Okay, let's double click. And because I have a 1215 controller, so I will save as this project and use one new project to replace this controller to i7-1215. Okay, let's go to the hardware area. Double click the device configuration. So the sample program use 1211 controller. I will change to my controller. So click this change device. Change to my controller, that is a 1215 DC controller. And the actual version in my controller, that is a version 4.4, which is higher than this. So that's actually I want to show. So firstly, the reason why I changed to the hardware, that because if you have one controller in your hand, this is the exact same way you will do. You will change to the device you have and match your hardware configuration. The second thing I would like to show, that is usually from Siemens' design, the higher hardware can support the lower firmware configuration. That means, for example, this version 4.4 actually can support the configuration version 4.0 to 4.3. So with this version 4.3 configuration, the higher hardware firmware can support this configuration. We can configure and download to the controller. The detailed compatibility of the hardware configuration, we need to check out the i7-1200 controller manual. Okay, I will configure 4.3 and let's click the OK. Alright, the system changed to my controller 1215. Okay, let's double click this Ethernet port to configure the IP address. Okay, I will configure my IP address to 192.168.1.200. That is my controller IP address. This i7-1215 controller, it has two built-in analog input channels and two built-in analog output channels. I will explain how we can scale the analog input and unscale the analog output using the following two videos. In this sample program, it is not using the analog input and analog output signals. It is using one function block as a simulated process object, or we can call that a controlled object. So in this program, we can only use the software to simulate this process. Alright, let's go through this sample program. And our main control loop, the controller, is named PID_compact. It is in this cyclic interrupt OB30. This OB30 runs as a cyclic interrupt organization block. So if we right click, go to the properties, so we can see the current cyclic interrupt, that is a cyclic time, that is 100 milliseconds. That means once this controller starts to run, this cyclic interrupt will run 100 milliseconds cycle time. Every 100 milliseconds, it will run one time. So all the program inside this OB30, they will be called every 100 milliseconds. Here it shows a red. Let's firstly compile this project. After the compile, it will correct these problems. Okay, in this cyclic interrupt, it calls this simulation process value as well as this core function block, that is a PID compact. And from this PID compact, we can click this small button. It will shift to the parameter settings of this PID control function block. There are a lot of settings here. From this commissioning window, it will go to this trained screen, which is very helpful because when we use the manual control or use the auto control or the fine tuning, we do need to see the train of the PID input and PID output to look at their control performance. So this trend is very helpful. Alright, I will use a step 5 video to introduce the detail of this commissioning window and the configuration window. Other than this PID compact function block, this simple program it also built up this PID HMI. With this HMI project, it's easier for us to understand what the basic control loop it looks like and what the basic function of this PID compact function block and how we can operate the PID control loop. For example, that is a trend for the set point, process feedback, and the control signal. Let's go to the next screen, the detailed parameters inside this PID. And next, that is the detailed parameters or the values of this function block PID underscore compact. As we can see, those screens give us a very good sample and a good template for the future project. That's why I want to use this sample program as a start. And to learn the detail of this sample program, don't forget you can download this document. This document explains the more detail how this sample program works. So in this video, the main target that is I will implement this sample program, make it run to show how it works. So I will compile this PLC project and download to my controller. Select the interface, start search. I find my CPU. Okay, the software found my CPU and I will hit this download. So when we download this controller, it will stop. Okay, download. Start. Now let's shift to the HMI. This HMI project that is based on the KTB900 basic, this HMI. That is a cost-effective 9-inch touch panel. That touch panel has keys on that. To run this touch panel project in our laptop, so we can use this simulation. Before we run this simulation, we also need to do one setting. So that setting will allow this simulated HMI project communicating with the actual PLC. So from here, let's go to the control panel of your Windows system. And if you install the TI Portal or Siemens software, it will build up one selection here, Set PGPC Interface. Click this Set PGPC Interface. So this interface plays a role how this software uses actual hardware communicate with external hardware. So the simulation HMI system will use this i7 online step 7, this access point, to communicate with the outside hardware. We need to point this i7 online step 7 point to the actual hardware. Sometimes if your laptop is communicating with a wireless communication, you need to point to the wireless network hardware interface. In my case, I'm using the RG45, the cable communicate with my PLC. That's why I'm pointing to my hardware network connection. When you select, make sure you select this TCP IP rather than this ISO. Make sure this. Okay, hit the OK. And then let's shift here and compile the project and start the simulation. Okay, let's hit this start simulation. Okay, once it starts, this screen will show as the same as the actual touch panel. As we can see, this HMI project already communicated with the actual PLC. So if we go to the corner button, it will show the PLC status. Current status, that is a run mode. Actually, this screen can be used as a template for your project. Okay, so this screen shows the actual control loop. This is our PID control, and the PID give an output, and this is the simulated process object, controlled system, and the system give a feedback, go to this input underscore PER, Currently, this system is activated. That means the PID loop, the controlled project comes from one simulated process. So the PID output is connecting to this simulated process input, and the feedback signal go to the input underscore PER of the PID compact function block. So this is an over picture of this PID loop. This is a scaling input and the scaling output setting of this PID control loop. We will discuss in the following videos. To switch the PID manual or auto, we will use this button to switch the PID control mode, manual or auto mode. Also, there are a couple modes, especially for this fine-tuning mode. It will allow this PID to fine-tune the PID 3 parameters. Okay? The third screen, that is a detailed PID parameters, especially for the gain, integral, and the derivative parameters are shown here. And from this trend, the green curve, that is an input signal. The blue curve, that is a PID side point. The output from the PID function block, that is a right curve. That is the whole train. Alright, firstly, to use this PID control loop from this sample program, let's go to the manual mode first. Let's shift to the system to manual mode enable on. This is the PID output under the manual mode. Currently, it's at 40. We can change the value to 35. Then this 35 will directly go to the output. So under the manual mode, we can directly control this output. Let's go to the trend. As we can see from this trend, this control signal changed from the 40 to 35. And the green curve, that is a feedback. And because this is a speed control signal, so once we decrease the output, the speed decrease. And the current PID parameter, the gain, that is a 1, and the integral, that is a 20. This is the initial parameters. Okay, so let's do a quickly demonstration. If I shift to this PID control loop to auto mode, let's see what the control performance. The current setting, that is a 510, that is a 1 speed setting. And this control mode showing here, that is an automatic mode. The actual number in this mode, that is a number 3. 3 means auto, which will be enabled when this manual enable signal goes from on to off. This is a falling edge. So once it's got a falling edge, this automatic mode will write into this PID controller. Change the PID mode to automatic mode. Alright, let's turn off this manual enable. That time, it will write this automatic mode into this controller. And from this output state, we will see the current is number 3. That means automatic mode. Okay, let's go to the trend. As we can see, this process feedback and output control got a strong oscillation here. Likely this gain is too high. We can decrease this gain. And let's change this gain from 1 to 0.4. And look at this performance. So this gain got a decrease, so we can see this output control got a ramp down, and this feedback green curve go to the side point gradually. But as we can see, the error between the side point and the feedback, this error is decreased too slow. So that means we can enhance our integral effects. That means the parameters of this integral value can be decreased. Okay, let's click this 20. So we can decrease this value. Let's see, from 20 to 10. Okay, so let's give a new side point from 510 to 550. So the system got an oscillation here. Likely the K is still too high. We can decrease the K a little bit. This is the PID parameter adjustment. So let's go to find where we can find these parameters. And let's go to the cyclic interruption. And let's hit the online. So you will see the actual values of this PID compact. We can click this button go to the configuration window. Let's see the detail. Then let's go to the PID parameters and hit the online monitoring. Those parameters are working inside the controller. Let's shift back to the HMI. We can compare. Those values are matched. Okay, let's shift to the parameter view. So from this parameters view, we will see all the parameters of this PID controller. We will find this gain, integral, and derivative value are set in here. So from this parameters list, we can see all the parameters. This is one method. Another method, we can go to this instant DB. We can find the instant DB of this PID controller and click this Open DB editor. This is the traditional DB online style. So let's find out where we can find this PID parameters inside this instant DB. Let's go to the bottom line, named retain. Let's open this retain, and you will find the gain, TI, TD, all those PID parameters are shown here. And those parameters will be retained with this checkbox. That means if the controller got shut down or cycle power, those parameters with a retain checkbox, they will not be lost. This retain is a very good feature of the Siemens controller because the controller doesn't need the battery to save the value. All those retained variables will be saved inside the retained memory. Alright, that is a configuration quick view. Let's go to the commissioning. Go back to the controller and let's hit this right button on the top of this function block. Let's click. It will transfer to this trace window. So firstly, let's set this sample time. I will select this 0.5, click the start, and start this monitoring. And we will see this is the actual process. If from the PLC side, if I change to the new side point, we will see the change. So we will see this online change. And one important feature I would like to quickly demonstrate, that is a fine-tuning function from this trained wheel. Let's go to this tuning mode. From this job list, we will see one is a pre-tuning, one is a fine-tuning, which can be used to automatically tune the PID parameters. To check out the descriptions of this PID tuning function, we can go to the online help of this PID compact. Let's hit the F1. And from this parameter state and mode V2, here, meanings of the value, it explains how this pre-tuning and fine-tuning works. Alright, let's go back to the function block and go to the commissioning window. Okay, currently our system is running in auto mode, and we will start to run this fine-tuning, which is a very good feature of this TI Portal PID compact function block. So it will fine-tune our parameters. When the system is working in a stable status and the process value is very close with a set point, we can start this fine-tuning. And click fine-tuning and hit this start. We will watch this process here. So we will see this process already started. I'm setting up 5 times speed of this video, so you can quickly see what the change of this fine-tuning process. So the right curve, that is a PID control signal, and the green curve, that is a process value feedback. As we can see from this trend, the right curve, that is a PID control signal. The PID controller now is controlled by this TI Portal system. Once we see this button highlight, that means the fine-tuning got finished. Let's go back to the parameters. The PID parameters got changed. The gain, that is 0.35, and the integral time, that is 1.1. PID sample time also got changed to 0.1. That's because this process is a quick process. That's because this is a speed control process, so it needs a higher sample time. Also, the PID controller is called from this cyclic interrupt. This cyclic interrupt OB30, that is 100 milliseconds cycle time. So the system automatically set this sample time to 0.1 seconds. Okay, so from here, let's assign a new value. So let's change to 550. So we will see the performance is really good. Let's change to a higher value. Let's change to 600. As we can see, they change to the set point very quick, almost no overshoot. And from here, we can zoom, make it larger. So from here, we will see which is very fast. So that means this fine-tuning works very well. After this fine-tuning, keep in mind the PID parameters. Let's keep this button, go to the PID parameters. So we will see the online parameters got changed by the system. To back up those parameters, we need to hit this upload. After we hit this upload, all those parameters are back up to this instant DB. And the system will show the difference. To match this difference, let's hit this download. Download this offline DB to the online controller. And after the download, it won't wipe up those parameters. We will see it's safe. But the system will show the match. Okay, this is basically the process. Firstly, we need to upload and then download this DB again to match the online and offline DB. We will see all those parameters are matched together from this start value project, start value PLC, and the online monitoring value. This is the actual value in the PLC. Okay, that is the sample program from this website PID control with a PID_compact for SIMATIC 1200 and 1500. This sample program can help you to quickly build up one control loop. Alright, that is our step 1. To leverage the PID sample program from this ID number, we can download the sample program, quickly build up the PID control loops, and then you can use this sample program to connect the actual analog input and analog output. So that's why in the next 2 videos, I will explain how we can build up the analog input and analog output. With this sample program, once you build up your own analog input and analog output, basically you can quickly build up one control loop. Okay, that is the first video for this whole series video, how we can implement PID loop control in the Siemens TI Portal system. Thank you for watching. Thank you for watching. If you like this video, please give me a thumb up. If you like to watch more videos in my channel, please subscribe and hit the bell. Thank you for watching.